Welcome back to Battleship Systems. Now that we've covered the basics of electricity, it's time to go over the main power system of a battleship. We'll cover power generation, switchboards, and distribution systems, including some probably never before seen photos of this equipment in its original configuration. Please check the errata page in the description. Unlike the fast battleships, the Battleship Texas is a DC ship, and that deserves its own special episode. So we'll be skipping the Battleship Texas and moving on to the North Carolina. The North Carolina ship service system uses alternating current, making the Battleship North Carolina the first AC battleship ever. For systems that still require DC, you would have to use a motor generator set, like the one we made in Basics of Electricity 4. In addition to the main engine turbines that propel the ship forward, machinery rooms 1 and 3 also have two smaller turbines that drive AC generators. These are called turbine generators, or turbo generators for short. The turbine uses 545 pounds of superheated steam expanded through 10 stages of blades. The turbine's rotational speed is controlled by a governor. The reduction gear reduces the speed to 3600 RPM to run the generator. The AC generator itself is a 2-pole, 450 volt, 60 Hz 3-phase generator rated at 1250 kilowatts. Fans circulate air through the enclosure as it passes through an air cooler. Water circulates through the air cooler and it cools the air as it moves through the generator. The stator portion is where the current is produced, and if you remember back to Basics of Electricity 8, we can vary the voltage of the generator by varying the magnetic field of the rotor. The rotor creates a magnetic field with 10 field coils that are supplied by 120 volts DC. However, this can be adjusted by the field rheostat. The rheostat consists of a series of resistors that are cut in or out by a moving arm. The actual rotor current is generated from the last piece of the turbo generator, the DC exciter. It's a compound wound generator rated at 10.5 kilowatts. It's of completely open drip-proof design. The generators have a shield over top to keep dirt from falling in. These turbo generators are wired directly into a switchboard. In the case of the number 1 machinery room, this is designated the forward turbo generator and distribution switchboard, while the number 3 machinery room has the afterboard. These are massive 2-story structures that contain metering, synchronizing equipment, controls, and circuit breakers for the 450 volt AC power and 120 volt DC power systems. Let's look at the wiring diagram for this board. As you can see, power from turbo generator 1 passes through metering coils and reaches a 2500 amp circuit breaker. Closing the circuit breaker will connect it to the total power bus. Among other things, this bus supplies power to circuits that are protected by these 1600 amp sectionalizing breakers. From here, it leads to smaller breakers that supply 450 volt loads, such as the power panels in the number 4 machinery room. These are similar to the breaker boxes you have in your home. Some feeders also supply 450 volt lighting circuits that consist of a 3-phase transformer to bring it down to 115 volts for shipboard lighting. It's important to note that this equipment is still functioning, and the battleship museums are able to power these boards with shore power. Shore terminal boxes on the main deck connect to massive cables that make their way down to the forward turbo distribution board. A 3000 amp breaker connects it to the total power bus. And yes, you can run the machinery that turns the 16-inch turrets with shore power. Not all systems can work on 450 volt alternating current though, and that's where the ship's service motor generator set comes in. 450 volt AC is sent to a synchronous motor that drives a 120 volt DC 125 kilowatt generator. That power is then sent back to the switchboard so it can supply power to equipment that needs DC, such as the 36-inch searchlights, battery charging, and other DC auxiliaries. But one 1250 kilowatt generator might not be enough power for us, so we have the ability to bring up the other turbo generator and cut it into the switchboard. However, if you remember back to Basics of Electricity 8, we can't just close the breaker and hope that it picks up the load. We have to make sure that the voltages match, the frequencies match, and that the voltages rise and fall at the exact same instant as our other generator. Otherwise, we will trip the reverse current device, which will forcibly open the circuit breaker. So after we match the voltage and frequency, we have to use the synchroscope to compare the oncoming generator's phase rotation with the switchboards. By adjusting the second turbo generator's speed with the governor control switches, we can make the synchroscope spin slowly in a clockwise direction. Then just before the needle reaches the zero position, we close the breaker. This process is called paralleling generators. After paralleling generators, we can use those same governor control switches to make one generator take on more of the load, even though doing so no longer actually changes the speed of the turbine. So this is great for the time being, but what happens when more motors and lights are turned on? The more load you have on a generator, the lower its voltage will be. Now you can adjust the field rheostat to produce more voltage, but then you'll run into an overvoltage situation when the load is decreased again. Here comes the automatic voltage regulator to the rescue. The voltage regulator is a complex device that monitors each generator's voltage and uses a motor to adjust the generator field rheostat, keeping the AC output voltage constant. Okay, so that covers everything on the upper level of the switchboard, but what's happening down here? So these are the larger motor-operated circuit breakers that are controlled from the switchboard above. There are two 2000 amp circuit breakers for the 16-inch turrets 1 and 2, a 2500 amp for each turbo generator, a 3000 amp for the shore power connection, and two 4000 amp breakers for the bus ties. So what is a bus tie? You can think of it as literally tying the bus of one switchboard to another. This will allow you to use the generators for one switchboard to supply power to more than one other switchboard. You can also combine active switchboards and have them share power in order to increase the kilowatts. However, before you close the bus ties, you have to follow the same procedure as you would for paralleling generators. To parallel switchboards, you have to match the oncoming voltage and frequency, then adjust the governors of your generators together until the synchroscope is at zero. Only then can you close the bus ties. The 4 switchboards on a battleship use what's called a ring bus system. This means that any switchboard can tie into the bus of the 2 neighboring switchboards, including the 2 switchboards on the extreme ends of the ship. So what about those other switchboards? Well, the North Carolina contains something rather surprising, something that no other battleship has. Buried deep in the lower decks are 4 massive diesel generators. These 1,350 horsepower Fairbanks-Morse 9-cylinder engines are the only part of the main power system not made by General Electric. They run an 850 kilowatt, 450 volt generator. Since a diesel engine spins slower than a turbine, this is a 10-pole generator. There is a forward and after diesel generator room, but their associated distribution switchboards are in separate compartments on first platform. Large breakers for the bus ties and other feeders are built into the control section. This is a great view of the forward diesel switchboard. You could even see one of the generator field rheostats mounted across from the switchboard. That panel way in the back is the bus tie to the forward turbo board. You know, it's really weird to parallel 850 kilowatt diesels with 1250 kilowatt turbos. I would think that one of those is going to have a harder time keeping up with load changes, but you don't have to take my word for it.
It was a live board that time. We were running a diesel, a forward diesel and one of the turbos together. They used to do that, which I didn't think was too smart a deal, because if one of the turrets would start up, they're 300 horse train elevation motors, you know, it threw quite a load on there, and the turbo would react differently than the diesel would. The turbo would pick up the load real fast, where the diesel was slow to pick it up. So there was a possibility you could possibly lose the load, you know. But they wanted to do it, so we did it.
So those are the generators, switchboards, and buses that make up the main power system of the Battleship North Carolina. Now we move on to the South Dakota class battleships, which for our purposes include the Massachusetts and Alabama. They had the same power systems for the most part. Each ship has 7 1,000 kilowatt, 450 volt turbo generators. They have 2 turbo generators in their number 1 and number 2 machinery rooms. The remaining 3 are distributed among the rest of the machinery rooms differently. For the South Dakota and Massachusetts, Machinery Room 3 got 2 turbo generators, while poor Machinery Room 4 only got 1. However, the Indiana and Alabama have 1 turbo generator in the number 3 machinery room and 2 in the number 4. There are no main diesel generators in the South Dakotas. Another interesting thing is that the foremost and aftermost distribution boards are not in the machinery spaces. They're in their own compartments on second platform, along with the 125 kilowatt DC motor generator sets. The distribution boards look similar to the ones in the North Carolina, but we see a built-in control cell that provides the operator with easy reach to the controls. We also see the concept of a load control switchboard. Since all the generators are the same, switchboard 1 has an amp meter for all 7 generators, allowing the load control officer to direct the power production as one big unit. After all, it has a ring bus system that allows you to use any number of the 1,000 kilowatt generators to work together. Switchboard 1 can also control the governors for turbo generators 1, 2, 3, and 4, while switchboard number 4 can control the speed of generators 5, 6, and 7. Very convenient. Now we move on to the Iowa class battleships, which includes the New Jersey, the Missouri, and the Wisconsin. The Navy went all out and gave them 8 1,250 kilowatt, 450 volt Westinghouse turbo generators. That's enough electricity to power almost 7,000 homes. These generators spin slower than the ones in North Carolina, so there are 6 pole generators, and each have a 16 kilowatt exciter. Westinghouse may not be as big of a household name as it used to be, but boy, General Electric sure is. Even though it doesn't exist by itself anymore, GE's legacy is sure to live on forever through our lifetimes. Can you count how many GE things there are in your home? Let us know in the comment section below, and don't forget to like and subscribe.
How about that, Bowser? We had plenty of spare GE bulbs all along. 60 watters, 75, night lights, and some of these handy 100 watters.
For me, it's the light bulbs, oven, and washing machine. Even though they aren't technically built by GE anymore, they still bear the GE name. Every engine room in an Iowa-class battleship has 2 turbo generators and 1 distribution switchboard. The distribution section is on the top, and the larger motor-operated circuit breakers are on the lower level. The controls are in a separate bench board that sits on the upper level. The master and load control assignments are the same as on the South Dakotas, but everything is located in the engine rooms, including the ship's service motor generator sets. I should also mention that since this is a battleship system, the circuit breakers have a special lock-in device, which is usually a knob. Screwing this down will hold the circuit breaker in the closed position no matter how high the current gets. Seems like a pretty dangerous feature, but perhaps not as dangerous as losing power and not being able to fight back. The power systems of the Iowa-class battleships have seen their fair share of modifications. They no longer have searchlights, so there's no longer really a need for a DC system. You also have to consider that there are no more 40mm guns, and they've all been shorted by 2 5-inch mounts. However, there have been many new power-hungry systems added, like air conditioning, radars, radios, firefighting pumps, new shore power terminals, sewage pumps, and all kinds of advanced equipment that didn't exist in the 40s. This video doesn't even go into what systems take over if the main power system fails, or one of the many smaller electrical systems on a battleship. We'll be saving those for another video. In lieu of donations to me, please consider donating to a battleship museum like the Battleship Missouri. There's a link in the description that'll bring you to the USS Missouri Memorial Association website where you can donate to the nonprofit organization. Thanks for watching.